Do I need to turn it on? No. Thank you. Okay.
Isn't finding,
Mhm.
isn't taking.
Okay, got it. Thank you. Yeah. Sure. Yeah, sure.
start. Welcome everybody to this week's ICTS String seminar.
Thank you so much for the invitation and the opportunity to speak here. So today's talk is going to be based on this paper in the archive with my student Vivek Singh at TIFR, and the work in progress with Harshit Rajgadia and Vivek Singh, both of who are again students at TIFR. Okay. So the talk will be about something called the canonical purification and related ideas and how they are related to bulk reconstruction, quantum extremality, and so on. So let me, just to get us all on the same page, let me define some of the words that I was using in this in the words that were used in the title. So if I give you a general bipartite state psi, and for the moment we can think about the state psi as when I say it's bipartite, I mean that it lives in a Hilbert space of this type, with one of which I'm going to call left and the other I'm going to call right. And for the moment, we can think of these Hilbert spaces as being finite dimensional. Of course, any such state can always be written in what is called a Schmidt form, where you have some numbers, p sub n, square root of p sub n, and then the vectors that you're seeing on the two sides are labeled by the same index n. Okay? They're not the same vectors. One of them, these guys are chi-n's, the others are labeled chi-tildes. So they're obviously some set of states or orthonormal states in these Hilbert spaces. They're different Hilbert spaces. They're not the same vectors. The way to think about these numbers Pn is that if you construct the reduced density matrix of the state psi on, let's say, either the left factor or the right factor, then these Pn's will turn out to be the eigenvalues of those density matrices. Okay. Of course, they are the same for both the left and right factors. The chi's and the chi-tildes are a choice of eigenstates for these density matrices. They're not obviously the same. Okay. So this is what I just said here. Now, on the other hand, let's say I don't give you access to the state on both the factors, but I only give you access, let's say, on the left. Okay. If you give, so that what that means is that I give you the reduced density matrix of the state on the left factor. Now, given that information, you can write down a purification, a bipartite state, let's call it psi star, which will have the property that its reduced density matrix on the left factor is the reduced density matrix of your state psi, again on the left factor. Okay. I've written down this purification very explicitly here. The chi-n's are the same old eigenstates from the previous slide. Chi-n tildes are the same old eigenstates from the previous slide. And these chi-tilde stars are basically another copy of the chi-tildes, but the star just means that there's some anti-unitary operator acting on them. And the idea is that the reduced density matrix has chi-tilde ket, chi-tilde bra, and you want to sort of flip that. You want to flip the bra to a ket to be able to write down a canonical purification for the state, and that's what this anti-unitary operator theta is doing. Okay, so this state psi star is called the canonical purification of the state psi, and then the language I'm going to use is I'm going to call this the canonical purification of the state psi with respect to the left side, which means I first construct the reduced density matrix on the left, and then I canonically purify it. Okay. You might notice that the state psi star sort of resembles the thermofield double state, and indeed, the thermofield double is the canonical purification of the thermal ensemble. Okay. In some sense, you can think of psi star as the simplest purification that you could build if you only had access to the left side of this initial bipartite state psi, where the word simplest is in quotes. It's not used in a technical sense. But given psi and psi star, since they are two different purifications, yes. Yes, exactly. You could define. More generally, you could define it with any unitary operator acting on this L star factor. So yeah, setting that to 1 in some sense is the. Canonical choice of this theta operator? Yeah, no, not. But I'm gonna, for example, pick something like CPT or CRT. Well, I mean, let's say if you're in even dimensions, there's a unit, an operator, an anti-unitary operator, which I can call CPT. I'm going to use that basically. Okay. If you have super selection sectors, then sure. Here, I'm not considering that situation. Here, clearly, there are no super selections.
What exactly is being purified?
What is being purified is reduced density matrix of this initial state psi on the left factor.
And in what sense is it a purification? Why do you call it purification?
Because it's this state psi star is a bipartite state on the Hilbert space H left tensor H left star, this thing I'm calling L star, such that if you trace out L star, then you get back the reduced density matrix on the left factor.
But even with chi r, I mean, even with the previous state also, you do the same thing, right? You just trace it out.
That's correct. So psi and psi star are two different purifications of the same density matrix on the left factor.
Yes.
So I'll say that in the next slide. Okay. Yes, you were making a comment.
But density matrix sometimes have, like some over superselection.
Yes.
Yes.
Yes. Yeah, if you have super selection sectors, maybe there are phase ambiguities, but sure, I'm not going to consider this. Yes.
We don't really have a common origin of time on the two systems. So if I added phases,
Good.
Good.
Yes, I agree.
You want to say this is canonical?
It's canonical in the sense that, if you, for example, if I hadn't put this theta here, then see the chi tildes, there is no canonical choice exactly because of the phase ambiguity that you're saying. Eigenvectors are not specified unless you specify their phase. Okay, so if I hadn't put this theta here, then whatever phase you pick for chi tilde will appear inside psi star. Because of this anti-unitary operator that's sitting outside here, those phases are going to cancel out. So that's in some sense, this choice is canonical because this theta makes sure that the ambiguity in the choice of phase of the eigenvector of the reduced density matrix on the left factor does not appear in this expression. Okay. Yeah. Yes, I'm going to say that next. Exactly. So exactly as Suvrat was saying, because these states psi, and one of the questions sort of pointed to this, because these two states psi and psi star are purifications of the same density matrix on the left factor, they're related by some operator on the right. So this curly R is an operator which only acts on this side, on the L star side. So just to point to something on this side, the L star side. Okay, and I've written out an explicit expression here. In the case where the initial state psi was full rank, this R is a unitary operator. More generally, it need not be. But the important point to emphasize is that it only acts on one side. In some sense, you can think of this R, this curly R, as quantifying how hard is it to reconstruct the original state psi given psi star. And for the lack of a better word, I'm going to call this operator the reflection operator. If you have any better suggestions for what I should call it, you should let me know. Why the word reflection will hopefully become clear as we go on. Okay, so why am I, so before I go into the technical details, let me just spend a few minutes explaining why I'm interested in studying any of these quantities. Why should I be interested in studying the canonical purification and this reflection operator in the context, let's say, of ADS-CFT? So one motivation, for example, comes from the fact that there is this interesting quantity called the reflected entropy, which has been studied recently following initially this paper, which is defined for some mixed state on two parties, let's say capital A and capital B, in terms of the canonical purification of that density matrix. So basically, what one does is one takes this density matrix, one canonically purifies it, and then studies the entanglement entropy of A star in that canonically purified state. And this reflected entropy finds a natural geometric interpretation in ADS-CFT in terms of.
Sorry, what is rho AB? What is rho AB?
At this point, rho AB is a mixed state on the Hilbert space AB. So,
but what are A and B?
There are two Hilbert spaces, the two factors, let's say.
Ah, two spaces. Okay.
Yeah. So, people have thought about how to quantify the entanglement between factors A and B when the total state is not pure, such as the case could be here. And this reflected entropy is one such interesting quantity, which turns out to have a natural geometric interpretation in ADS-CFT in terms of the cross-sectional area of the entanglement wedge of AB. Okay. So for my purposes, I'm not going to talk a lot about, I'm not going to talk at all actually about reflected entropy, but I just thought I'll give you some reason to believe that the canonical this is one place where the canonical purification enters the discussion in ADS-CFT. Okay. A second, yes, please.
So you are not saying that the complexity in constructing psi from psi star somehow has a geometric interpretation in ADS?
Well, that would be wonderful if it does, but I mean, here I was making a much more limited statement. Here, I was saying that if you have a bipartite mixed state, rho AB, then there is something that you can compute in its canonical purification, namely the entanglement entropy of A star, which has a geometric interpretation in ADS-CFT in terms of these this cross-sectional area of the entanglement wedge of A. It would be wonderful if the reflection operator itself had some nice geometric meaning. I will tell you to what extent we understand this. Yeah.
But what you want to calculate is this complexity from.
That would be wonderful. Yeah, that would be ideal. That's where we are headed with this. Yes. We are not there yet. Yes. Okay, good. Another motivation for studying the canonical purification comes from thinking about evaporating black holes. Now, in a situation where you have an evaporating black hole, let's say past its space-time, there's a lot of entanglement between the black hole and the Hawking radiation, but this entanglement is not geometrized, right? There is no, in the sense of ER equals EPR, there's no spatial wormhole connecting the black hole with the radiation. But it was argued in this paper, this nice paper recently, that indeed the canonical purification of this black hole radiation state with respect to the black hole, or from the side of the black hole, has a connected ER equals EPR wormhole in it. Okay, we'll see where that wormhole comes from in a little bit. But the idea then is that this operator curly R, the thing that we call the reflection operator, in this specific case, what it does is it sort of takes all this entanglement between the black hole and the radiation, and it geometrizes it into an ER equals EPR wormhole. R, in the way I defined it, takes psi star to psi. Yes, that's right. Yeah, but okay, R in R dagger. You can. Yeah.
The fact that the canonical purification of and the canonical purification.
It's similar, but it's more related to the fact that there is a nice prescription for in ADS-CFT for what the canonical bulk dual to a canonical purification should be. So I'll get to that in a couple of slides. Maybe there you'll see it more explicitly. Okay, so my main motivation for studying these quantities comes from entanglement wedge reconstruction and thinking about it from a quantum error correction point of view. Okay, so let me for this I'll have to give you a little bit of technical detail. So let's say that you have some holographic CFT, again a bipartite state on L and R, and you have some bulk degree of freedom in the entanglement wedge of R. Okay. For simplicity, I'm going to think of this bulk degree of freedom as being labeled by some set of states, which I'm going to use the label I for. This is sort of my code subspace for this bulk qubit. And the corresponding set of boundary CFT states are going to be called psi sub I. So the same label I appears here. These psi sub I are boundary CFT states on this H left tensor H right Hilbert space, such that the bulk qubit is in the state I, little I. Okay. Now what I do is I introduce this auxiliary reference system that I've written here, and I write a maximally mixed state between this auxiliary reference and my holographic CFT LR. So for the moment, think of this as a sort of technical tool, an auxiliary construction, if you like. We'll see the point of doing this in a slide from now. Okay, so for now, let me define psi as this maximally mixed state between this reference, which is some auxiliary system, isomorphic, of course, to the code subspace, and the holographic CFT. Yeah, it's a d-dimensional Hilbert space. Yes, it doesn't matter. We can take it to be qubit. I'm not sure. Let's take it to be a qubit. Okay. Now the statement that this qubit is in the entanglement wedge of, let's say, the right system is equivalent to the statement that the left system knows nothing about the reference qubit. Okay. That is because this reference qubit is maximally entangled with this bulk qubit, little I. And because it's maximally entangled with this bulk qubit, which is in the entanglement wedge of R, it couldn't share any entanglement with L. Okay. So the left side knows nothing about this qubit. This is you can use the Ryuta-Kainagi formula to just check this. This is just the statement that there's no mutual information between the left system and the reference system. You can just use the Ryuta-Kainagi formula to check that. But I'm not going to go into the details of that. But take my word for it that the statement that this bulk qubit is in the entanglement wedge of R is precisely equal to this. Okay, and you can check this using the Ryuta-Kainagi formula. All right. Now, once you know this, then you can do something nice. So let me try to construct the canonical. Yes. It's outside somewhere. Outside of it. Yes. Yes. I should have said that. Yes. This is the partial trace of this with respect to right. I should have said that. Yes. Yes. Let's say yes.
Now you say
correct. Yes. Yes.
Now this L is the rest of the CFT.
Yes. I can just draw. L knows nothing about the reference. That's the statement. So this is L. This is R. Let's say there's some qubit here, and I'm introducing a reference system, which is, let's say, outside. It's some auxiliary thing. And then I'm maximally entangling this qubit with the reference system. This qubit? It doesn't, because it's in the entanglement wedge of R. That's true. That's true. That's for sure. But I'm maximally entangling it with this reference system. Yes.
And this thing was
yes. Okay. Okay.
And then it,
Yes.
so now you use some Euclidean.
Yes.
It is entangled with something in it.
I mean, it's hard to say that because it's sort of something that's this is encoded in R, right?
Encoded in R, but R itself is entangled.
That's right. That's right. That's right.
This is the degree of freedom.
Sure, but basically what the idea of this construction is that once you sort of this reference system is sort of supposed to like be a sort of tag for this bulk qubit. Okay.
So you're saying that this is kind of a definition that you need to use.
Yes.
Not in it.
Yes,
It's not
that's right.
something that follows from some.
No, this is what is called the decoupling principle in quantum error correction. So if, for example, you can just use, so this statement is the statement that the mutual information between left and ref is 0.
Depends on
Definition was inside left. No, but it's not. It's so ref is some auxiliary system.
I understand.
Yeah.
But
Okay.
the thing is, it would have been
Yes.
maximally entangled with something inside.
Yes.
By construction is not inside.
That's correct. Yes, that's right. Yes, that's right. That's by
So
construction.
they are
Correct.
changing the state.
Yes, I am changing the state because this capital psi is a different state. Right? I'm looking at a different state, which is this capital psi. That's exactly right. Yes, and you'll see in a bit why I'm interested in capital psi. Yeah. But
I have a naive question.
Yes.
Since L and R are entangled, I mean, it might not be maximally, they are not maximally entangled, but since they're entangled, why doesn't this reference state, which you're entangling with R, also doesn't get entangled with L?
It's because the technical reason that happens is because this reference system is just entangled with this particular qubit, and that qubit is somehow encoded in R. I mean, if you walk through this, if you just compute this mutual information, let's say using the Ryuta-Kainagi formula, because the mutual information is just is a sum of terms involving entanglement entropies. Each one of those you compute using the Ryuta-Kainagi formula, and you'll find that this is 0. Precisely because precisely in the situation where this qubit is in the entanglement wedge of the right system.
Yeah, but this this reference state is sort of a dual, right? Isn't it dual to the R?
No.
I mean, in the sense of ADS-CFT?
No. Reference is just some. Okay, so think of the bulk. There's some bulk degree of freedom which is a qubit, and the reference is just another qubit, which I am introducing by hand and maximally entangling with this bulk qubit. It has nothing to do with the bulk state.
But doesn't the Ryu-Takayanagi formula say that the bulk wedge, whatever exists in the wedge, is kind of the dual to the thing that is on the boundary?
That's right. But it's not this reference system. It's the qubit, which is in the entanglement wedge of R. That's a different system as compared to this reference system.
Okay.
Yeah. All right, good. So
this sum over I is running over how many?
It's, let's say, whatever the bulk code subspace is. So if you had a bulk degree of freedom that you wanted to reconstruct, let's say it goes from 1 to 2, then the sum over I will be that. So this reference system is exactly isomorphic to the code subspace. Okay, good. Now, once you know this fact, then you can do something nice with this idea of the canonical purification. So let me take this initial state psi, this capital psi that I've constructed for you, and let me try to canonically purify it with respect to reference and L. Okay? I'm going to think of this capital psi as a bi-partite state between reference union L and R. Okay, reference union L is one side, R is the other side. It's a bi-partite state from that point of view. So I can write down the canonical purification psi star from the point of view of reference L. So now there is a second copy here, which is reference star L star. Okay, And this is exactly this formula is the exact same formula that I had written down for you for the canonical purification 2 slides back. Except the one thing that's new that I'm using here is the fact that each one of these states, which are supposed to be the Schmidt eigenvectors from the left point of view, each one of them are factorized. So you see, each one of these things is something on reference, tensor something on L. Okay, that comes from this statement. The fact that the density matrix on ref and L is factorized. Okay. So I've used this factorization statement over here in writing the canonical purification of what I call capital psi. And from our previous discussion, of course, capital psi and capital psi star are related by some operator, the reflection operator, curly R, acting only on this L star factor or this factor, one side. There is no, yes, exactly. I mean, that happens because actually, so strictly speaking, there should have been some P sub M's corresponding to the left and some, let's say, Q sub I's corresponding to the ref. But since the reduced density matrix on the left, on the ref is maximally mixed, they're all equal. So I just factor it out. Yeah. Yes. Yes. Correct. Correct. Yes. In general, it's on ref star L star. It's in whatever, which is what. So here I'm thinking of ref L as one side. I'm purifying it. So in general, the reflection operator will act on ref star L star. Okay. It's whatever is the other side. One side was ref L, the other side is ref star L star. So it's going to act on ref star L star. Yes. So reflection operator is not unitary. Yeah, that's fine. I'm not using that. I'm not using unitarity. Okay. But the only thing I'm saying is that it doesn't act on this side. Whatever it is, it acts on the other side. Okay. Okay, good. But now I claim that this operator R, this curly R, lets you do bulk reconstruction or entanglement wedge reconstruction. The reason for that is that from this state, I can just project, let's say on the ref factor, I can just project on the ith basis state. Okay. Because this curly R only acts on reference star L star and not on this side. Okay. The projection operator just trivially goes through this R and hits psi star, where it just projects you into the ith basis state on ref. So you learn that psi I is nothing but this reflection operator acting on I star reference star times some state chi on LL star. The chi is basically the square root of PMs summed with M on L and M star on L star. Okay. Yeah. L is one side of the CF. Yes. Let's say it's on a sphere. Exactly. So yeah, I mean, for example, I mean, yeah, let's say you put some UV cutoff to make everything finite dimensional. Let's say you do that. Yes. Then there was L and there was L. L was one side of the CFT, and L star is the thing that will the purification. Exactly. Okay. What? Yeah. References. Yes.
So you had a Q date and its reference, and now you look at the purification.
Yes.
Which could have given back the reference, but has given you something.
Yes, exactly. So what this has done is that it has, in some sense, it has sort of distilled out the Q date which was in the bulk in some auxiliary sense. It's sort of distilled it out into some auxiliary system called reference star, left you behind with a holographic CFT state on LL star, which I'm going to call chi. And now there's this operator sitting out front. Okay, the way you should think of this is that this operator, this I star is like, some bulk qubit which is sitting out at infinity, or away, actually not in the CFT, but outside of the CFT. You bring it, you couple it together with the CFT state on LL star using this operator. Crucially, this operator only acts on one side, on the L star side, not on the L side. Okay, you couple it together with the L star side of the CFT state using this reflection operator, and that's what gives you back the bulk state that you were interested in. Okay? This, by the way, this formula here is basically Harlow's reconstruction formula. The way Harlow thinks about ADS CFT as quantum error correction, this is just that formula. Yeah.
Why is this L important?
Why is the?
One copy of the CFT.
Well, yeah, sure. You could do it with one copy, but for my purposes, I'm emphasizing L because I want to think of this as entanglement wedge reconstruction, right? So suppose you have some bulk qubit which is in the entanglement wedge of some subregion, then I can reconstruct it only on that subregion.
Okay.
Yeah.
Then I can just.
If you want, yeah. I mean, this also works in the case that there is one copy. I'm saying more generally, it works in the case where there is a complement. And the important thing to emphasize in that case is that this curly R will not act on L. Okay. Yeah. This is the curly R is the reflection of the thing that this thing. The thing that maps the canonical purification. So the state and its canonical purification, the operator in between them is curly. Yes, physical purification, exactly, yes. The operator that maps the canonical purification to the physical purification. Yeah.
Chain of like purification that we have.
Yes.
Then you have the canonical.
Yes.
Which was just left.
Yes.
Now you add this R.
Yes.
On the left.
On this side, reference star L star.
So when R acts on reference star, it gives you back reference. Sorry, back the qubit.
It gives you back the qubit, exactly.
I see. So when R acts on reference star, it gives you back.
Yes.
And when it acts on the remaining.
No. So R naturally acts on reference star L star. Okay.
And it gives you.
And then it gives you the qubit which was encoded in R. Yeah.
So why is this? I'm confused. Why is this a very useful formula?
Yeah.
R is the operator that is. How does it know what the physical purification?
How does it know? Well, I mean, for example, more practically, if you wanted to write some operator, let's say little phi on the code subspace, then I could, reconstruct that operator little phi on the system of interest, which is this right system, by writing this formula, right? Yeah.
How you write R.
Yes. Yes. So that's the whole point. In some sense, we want to develop tools to be able to write efficient formulas for this curly R. Yeah.
R is not even an operator in the right CSP, right? In the right.
It is. I mean.
Something that it acts on this.
Yes. Not reference. It maps the reference star L star system to the R system. So in particular, what R dagger will do is that it will map the right CFT to the reference star L star system. Then you will act this phi on the reference star system, and then R will map you back to to the right system. Okay, so this whole thing is as an operator on the right system.
Yeah. Let's say if I can solve this.
Yes. Okay. Yeah, I will get to that. So okay, just to look ahead a little bit, in the gravitational case, there's a replica trick for R. You can write down the replica trick construction for R. What I'm going to talk about in this talk is I'm going to talk about how to write down formulas for R in a setting where there's a one parameter family of states. So I'm going to try and write down a flow equation for this operator R, which is going to give me some control on how to compute R.
But we see the bulk, like when it repeats this again
No, not using. So not in today's talk, I'm not going to use the bulk. I'm going to write down a CFT formula for R.
But what I'm saying is,
Yeah.
like, it's not a use bulk reconstruction, bulk reconstruction.
No, the replica, you're referring to the,
What you're saying.
okay. Oh, yes, I agree. Yeah, that's not the point. The point is to write down a CFT formula for the reflection operator, which will then give you the bulk reconstruction. Yeah, I agree with you. Any other questions? Okay, so this, sorry, I'm sorry for this long discussion, but I thought the main point that I should convey to you is that the canonical purification and this reflection operator is a useful tool in ADS-CFT, in particular if we can find efficient ways to compute them. Okay, they allow you to do entanglement wedge reconstruction quite efficiently. And in particular, it would be really wonderful if we can answer Ashok's question from that perspective by thinking about the complexity of R, for example, which is still far away, but still. Okay. All right. Now, one of the things that's nice about the canonical purification is that it has a nice geometric dual in ADS-CFT. Okay. So let's say that there was some state on LR, the thing that I was calling capital Psi, which has a geometric dual, which I've sort of, the Lorentzian geometry is pictured here on the left side. Okay. Engelhardt and Wall claimed or argued that a natural bulk dual for the canonical purification of this state would be to take the entanglement wedge of the left. So I've redrawn the entanglement wedge of the left over here. And instead of putting the entanglement wedge of the right on this side, you put a CPT reflected copy of the entanglement wedge of the left on this side. Okay. So you take the entanglement wedge of the left, you glue it to its CPT reflected image at the quantum extremal surface. The quantum extremal surface here is the codimension 2 surface, which extremizes the generalized entropy. Okay. Yes, exactly. Exactly. So now you can see that, even if this right system had no, even if the, yeah, exactly. So if you use this this prescription in the case of an evaporating black hole, you would end up with a connected geometry. Okay. Now in gluing together,
Hey, I had a question actually. Could I just ask a question quick?
Yes, please.
Okay, so in this case, we're gluing it on an extremal surface. Is that right? So we're gluing it on an extremal surface. And this is a codimension 2 set of conditions. So we're concerned with the extremal surface in itself, not the slice in which it's contained.
Yes.
Okay, so I think you actually might be mentioning this. I'm just asking it because I'm not sure what the talk's next aspects would be. But in the paper you had written, you had mentioned that there's a delta function because it's a quantum extremal surface and it's a result by Busso that tells you that you need to have a delta, you need to have a shock. So so when you say that there's a shock, are you saying that it's on the entire null slice or it's only at the extremal surface where you're gluing it?
We'll come to the shock in a bit, but yes, the answer is that it's on the entire null slice.
Okay, so the entire geometry of the null slice would be actually affected.
Yeah, I mean, the shock sort of supports. Okay, I'll come to this. Maybe hold on
Yeah.
for 1 or 2 slides, and
Yeah.
All right, good. So what I think, okay, to continue, the idea of Engelhardt-Wall was that there is a geometry you can write down, which might at least have the desired properties of the canonical purification. But of course, when in gravity, when you glue together 2 pieces of space-time, you have to make sure that the junction conditions are satisfied. That's required for this geometry that you're going to construct to solve the equations of motion, Einstein's equations. Okay. Now it turns out that for the junction conditions to be satisfied, what happens to be the case is that if the surface that you're gluing across is classically extremal, then these junction conditions are trivially satisfied. Okay, essentially the junction conditions involve the null expansions of this surface across which you're gluing. For classically extremal surfaces, the null expansions vanish. This particular dA by dx plus or minus is 0, and so the junction conditions are trivially satisfied. Okay. In particular, you don't need any extra matter stress tensor on the quantum extremal surface or the corresponding null slices for this geometry to be supported. However, when you include quantum corrections, there's a problem. There's a slight issue because when you include quantum corrections, the quantum extremal surface does not satisfy dA by dx plus equals 0, but there is a quantum contribution. Okay, so in the presence of quantum contributions or quantum corrections in the bulk, it turns out that for the junction conditions to be satisfied, you need to have a stress tensor, a bulk stress tensor, that is supported on sort of these null slices and with a precise coefficient. Okay, you need a stress tensor shock in the bulk for this geometry to satisfy the Israel junction conditions, and in particular the Einstein's equations. The coefficient of that shock is an order 1 number, which is given by this in terms of the bulk entanglement entropy, like so. So I hope that this answers the question that was being asked. This is the shock?
Yeah, I mean, yeah, somewhat similar. Actually, it was just a geometric question in general, because if I say just, considered maybe some case where I had some, I mean, if I had some wedges, so I'll just call it the way you had mentioned it. So there's a right wedge, there's left wedge, and then there's 2 other wedges on the top and the bottom.
Yes.
So when I'm gluing these 2, the right and the left wedges, I'll have the top and the bottom wedges that satisfy some constraint equations, and those are fiduciary regions. In this case, is there any precise formulation for what the top and the bottom wedges should satisfy, or is it as trivial as so?
So what you do is you write down the standard Israel junction conditions for the gluing between the top and the right wedge, let's say, across the null surface, and then again the bottom and the left wedge, and then you take the limit of these junction conditions as you approach the quantum extremal surface, and that's what this condition here is. So this condition is written down at the quantum extremal surface, but the way it's derived is by using the codimension 1 junction conditions and then taking the limit as you approach the codimension 2 surface.
Mm-hmm. Okay, and if let's say I was being a little adventurous and I was doing it in the case of some black hole space-time, where the top and the bottom wedges are precisely defined as the interior region. So would the null slices that contain the horizon, would their geometry change, or would that be just somewhat static?
Well, so what happens in this canonical purification is that the geometry to the future, what you call the top and the bottom wedge, is sort of that is determined by solving the Einstein's equations. What would be the case is that the geometry in the right and the left entanglement wedges is unchanged, it's this picture. It's unchanged in the sense that it's determined by this, and the shocks are necessary for the evolution of this geometry into the top and the bottom wedges to satisfy Einstein's equations.
Okay, so it doesn't matter which null slice it is. You can simply write down the equations for the codimension 2 junction conditions.
No, it's well, I mean, it's the null slice that is pertinent to the entanglement wedge of the left. So there are these null slices in the entanglement wedge. These get duplicated, and then so you have these natural null slices, and that's where the shock is supported.
Yeah. Okay, that's good.
Okay, great. So the point is that in the case where the gluing happens at a quantum extremal surface, which is not classically extremal, there's a shock in the bulk. Okay, the shock is a quantum shock. It's an order 1 shock. So what I'm going to do is I'm going to in this talk, much of it is over, but still, the goal of this talk was to sort of use the techniques that I had tried to introduce, tools such as the reflection operator and the canonical purification, to show from a CFT point of view that the bulk stress tensor in the bulk dual to the canonical purification indeed has such a shock. Okay, that's the point. That's the thing that I'm going to work towards. I'm going to do this in a perturbative context. You'll see what that means. But along the way, we're also going to try and see, try and use some of these tools and techniques to try and write down hopefully useful formulae for entanglement wedge reconstruction. Okay. So going ahead, what I'm going to try and do is I'm going to try and derive I'm going to imagine that there's a one parameter. Okay, so let me just say it. I'm going to imagine that there is a one parameter family of states psi lambda, again in this bipartite setting, and the aim will be to try and derive a flow equation for this reflection operator and the canonical purification, and towards where we are heading with this, at least in this talk, is to try and verify this prediction of Engelhardt and Wall that in the quantum context there needs to be a shock in the bound. Okay, that's where we are headed with this.
Canonical purification.
It has an order 1 shock in the Bout stress tensor. In the singularity meaning, it has a delta function stress tensor.
They become worse enough to have application similar.
Yeah. Yeah, I mean, it could become worse in the top and the bottom wedges, for example. When you take this initial data and then evolve it using the Einstein's equations, then you get what you get, and you could end up with crazy singularities.
So can I say that canonical purification you're saying has a firewall? So the physical purification
may not. Yes, exactly. That's right.
So this the job of the OR operator is to dissolve.
That's right. That's right. That's exactly right. Yes. That's right. That's correct. Yeah. That's right.
But this is a well-defined question. You think there's actually a well-defined shock that you can.
Yes. Yeah. With this particular coefficient, and this statement is just Einstein's equations. It's nothing more than that.
And a particular choice of how you do CP.
Yes, that's right. That's right. Any other questions? Okay. So yeah. Sure. No, go ahead.
Let's say take the eternal time.
Yeah.
And you do a time translation on one side.
Yeah.
Which is like a purification.
Yeah.
Then you're roughly Q.
Hmm.
In fact, you might have thought that there's some jumping condition. But in fact, the full state of the bulk is completely smooth.
Yes.
The whole thing is completely smooth.
Sure.
And that is not relevant for the string of fluid. Get rid of some of the stress tensor by doing something.
Well,
if you thought about it wrongly,
okay.
this key on quantum field here, you might firewall the key.
Okay.
Because
Okay.
But in fact there is no firewall.
Uh-huh.
That's because
well, okay. So as I said, this statement here comes from Einstein's equations, right? Now, so it's a statement that's diffeomorphism invariant.
this issue of the canonical purification relying on some choice of CPT operator and so on, you're saying that.
Yeah, I mean, all that it really relies on is how CPT acts very, very close to the quantum extremal surface. Very close. Yeah.
And so you couldn't do something, for instance, that all will go into the details of.
Well, okay, yeah.
Maybe a rephrasing, correct me if I'm wrong. If you use this stress tensor and
Yes.
you try to solve for the bulk equations of motion,
Yes.
the original metric that you had without this source and the new one are not related by diffeomorphism. This is a nonlinear thing.
Right, but I mean, yeah, exactly. It's with this stress tensor, the equations, the geometry that you get is basically this one. It has entanglement wedge of the left glued to the entanglement to its CPT image at the quantum extremal surface. And then, this equation is basically just telling you that this particular gluing status is well primed to solve the Einstein's equations. It solves the Einstein's.
And before you inserted the stress tensor, the solution was on the left. Or
before
the image on the left.
That's right. This thing here is the entanglement wedge of the left coming from the original state.
I think now it's
Okay.
I guess in this case we know it.
As far as I know, yeah.
And this particular stress tensor, I'm not sure. I know this is any energy.
No, it satisfies the conservation. Is that what you mean?
Does it satisfy like?
Oh, no. Yeah, that's right. Yeah.
So it could be like some completely negative energy state and this having to be bound and can create all sorts of random particles and.
Well, I mean, it's related to, so, the shock is related to, for example, the coefficient is not completely arbitrary, right? This coefficient is something specific.
But what I'm saying is, it will not be positive, or it will not.
I think it will satisfy some lower bounds. I mean, it will not be arbitrarily negative. It will, yeah, I think it will become clear.
For example, does it satisfy average
the average. Yes. It satisfies. So right. Yes, I think it does that. Yes, I think so. Yes.
Okay.
Yes.
Okay.
Yes. Yes, I think so. Yes. So let me see. So
because if you integrate this over, like x plus.
so if I integrate over x plus, then it's just going to pick up this thing over here, and yeah, you're right. It can take either sign, but so it sort of satisfies these generalized energy conditions. So, like for example, there's this half average null energy condition, which says that the integral, let's say from 0 to infinity of t plus plus, not minus infinity to plus, 0 to infinity, has to be lower bounded by this number here, right? Delta s by del x plus. So indeed, you're right. It can become negative, but there is something that is bounding it from below. This is again in the same spirit as the Q-neck, and this half I neck is an integrated version of the Q-neck. And so on. It can become negative, but not arbitrarily negative. Yes.
This guy is not really divergent on the right hand side.
This guy. You will see that in the context that I'm working in, it will not be. It will be something. Well, yeah, you'll see that. What I'm going to do is I'm going to work in a perturbative context where this delta S bulk by del X plus can be well defined, and in particular, I'm going to define it by subtracting of the vacuum contribution. Sure. That's sort of where it came from. That's sort of where it came from. Yeah, but the way I'm going to define it is by subtracting of the vacuum contribution, or the contribution in the sort of background state. I'm going to work in a perturbative context around the thermofield double state, and I'm going to define this thing by subtracting of the background, the thermofield double entanglement entropy, which is going to allow me to make it well defined.
Okay, so just finally, just one last question. So what the implications of this is that you identify the right wedge, the left wedge, and then you evolve them, find the top and the bottom wedges, and then you glue them all together. Is that right?
That's correct. And it all holds together, and you get a well-defined geometry in the bulk with a prediction for what the bulk matter stress tensor has to be in particular, a prediction for a shock contribution from the bulk matter stress tensor with a precise coefficient. And what we are going to do in the rest of this talk is to try and derive this by using the techniques that I mentioned, such as reflection operator and so on, but from a CFT point of view. So this was a prediction coming from GR, from the bulk point of view. And the aim is to try and derive it from the boundary point of view by trying to develop some tools to compute using the reflection operator.
Okay, thank you.
Okay, good. So the way I'm going to approach this problem, at least in this talk, I mean, ideally, it would be nice to have broader set of tools to compute these canonical purifications and reflection operators. But in this talk, the approach I'm going to take is I'm going to imagine that there is some one parameter family of states in this left-right system, which you can think of as, for example, let's say lambda equals 0 is the thermofield double state. It has a nice geometry dual to it. And then I deform away from the thermofield double state. This lambda is some parameter which deforms away from the thermofield double state. Okay. Now, at any value of lambda, you can, of course, compute the reduced density matrices on the left and right factors. These would be row left and row right as functions of lambda. And correspondingly, I'm going to define the modular Hamiltonian as minus log of these density matrices. Okay, so k left is minus log of row left at lambda, k right is minus log of row right at lambda, and so on. Okay, so now at any given value of lambda, of course, we can talk about the eigenvalues and eigenstates of these modular Hamiltonians. Okay, these chi-n's and chi-n tildes I'm using the same notation. These are the Schmidt vectors that I was talking about before, and the reflection operator is given by this particular operator over here. Okay, and it's a function of lambda. Now, in order to derive some kind of a flow, so the aim is to derive some flow equation for this reflection operator that will let me do some concrete calculations. So that's not very hard. So for example, you can derive a flow equation for these eigenstates by just doing sort of time-independent perturbation theory. Okay. And then what I'm going to do is I'm going to write this formula in a convenient way by exponentiating the denominators by introducing a Schwinger parameter. So the t here is a Schwinger parameter that I've used to exponentiate this thing in the denominator. And going from here to here, what I've done is I've introduced, in using the Schwinger parameter, I've used sort of a cutoff, a regularization, if you like, which is this e to the minus epsilon t. I'm going to send epsilon to 0 at the end of the day. And going from the first line to the second line, I've just introduced the added and subtracted the m equals n term to write it in this way. There is the m equals n term comes with a 1 over epsilon, but of course the sum of these two does not have that term because m equals n is not included. So the divergence here cancels out the corresponding divergence in this term. The only reason to write it in this particular form is that this second term here is an overall phase. Okay, it's d chi n by d lambda equals some number times chi n. So this thing here is an overall phase. It's sort of, you can think of this as the abelian part, and this here, now what's left over is some operator which is entirely written in terms of the modular Hamiltonians. Okay, so this is just a convenient rewriting. We can. So what I just told you is that there are flow equations for these eigenstates of the modular Hamiltonians, which you can write down in this particular way. And these curly AR and curly AL are just what I showed you here, except that now this overall phase part, I'm labeling little a and little AR and little a left. It turns out that these guys, the phase parts, the abelian part, at the end of the day are going to just drop out of our calculation. So they're not super important. That's why I chose to rewrite these equations in this form. And written in this form, you can sort of start to identify or think about what these curly A's are. These curly A's you can think of as connections or defining a connection a connection on a bundle of this type of U dim H left times U dim H right, the way to think about why they are connections is that instead of starting with the state psi, you had started off by considering some other state psi prime, which was some unitary U, let's say, acting on one side, let's say on the right side, on psi, but let's say that this U is a function of lambda in general, then you would, by just going back to these definitions and reworking them, you'd learn that the way these curly A's transform is this in this particular way. This is probably not super hard to imagine. So these curly A's transform under actions of one-sided unitary transformations in this particular way. Okay, and the same formula is also true if the one-sided unitary transformation acted on the left. Okay, so you can think of these curly A's, curly A left and curly A right, as some kind of connections. Sometimes people call these modular Berry connections. Okay, and using these curly A's, you can write down a more or less simple flow equation for the reflection operator. Okay, so now here's a flow equation for the reflection operator in terms of these modular Berry connections. The thing to emphasize perhaps about this equation is that these modular Berry connections only depend or can be entirely written down in terms of the modular Hamiltonians. Okay, if you give me the modular Hamiltonian as a function of lambda, I can explicitly, at least in principle, compute the modular Berry connections. Up to these phases, as you'll see, eventually drop out. Okay, and of course, now this flow equation can be solved, at least formally.
Sorry. What are the A's? A's in the right-hand side on the previous slide. What are A's in the previous slide? What there are in the right-hand side?
These A's or these A's?
In the right-hand side, yes.
Are you talking about the little A's?
Yes.
Oh, they can't see the pointer. Okay. The little A is basically you can think of the little A as the phase part in this equation. So on the right side of this equation, there is this part, and then there is a phase part which I separated out.
Thank you.
That phase part is the little A.
Thank you.
Yeah. Yes.
There's possible Euclidean method.
Yeah. So this is going to give you a much more explicit. This is going to give you an explicit formula in one slide.
More explicit.
At least in my opinion, yes. Yeah. Yes. So that formula is sort of an in-principle formula. You take the boundary operator, you modular evolve it, and then you try to find some inversion for that formula. So here's okay, one in like towards the end of the slide. So what we've shown is that there is a flow equation for this reflection operator. That flow equation can be solved. It's in a formal way using these sort of holonomies or these sort of Wilson lines for these modular Berry connections. And now if you take this formula and you plug it into your, as Subrat said, there was a formula for bulk reconstruction in terms of this reflection operator, right? If you plug our flow equation, solutions to the flow equation into that formula, you get a very explicit formula for the bulk reconstruction at lambda in terms of the bulk reconstruction at lambda equals 0. Where this the UR, let me emphasize, is explicitly written in terms of the boundary modular
Modular Hamiltonian, right?
Oh, yes.
Modular Hamiltonian of R.
Yes.
But why is that different from the?
Yeah, but it's an in-principle thing. You have to modular evolve, and then because you have to modular evolve it, compute the correlation function, try to invert that correlation function. Yeah, it's not immediately clear in their construction whether you can invert it clearly or not. And for example, the thing that they do very explicitly is that they're able to write down the modular 0 modes. Right? That's the thing they can do very explicitly. Here, this formula is just completely general.
But the difficulty is, of course, that we don't know how to compute the model.
Correct. That is correct. That is correct. So yeah, this is I would not say that this is conceptually different from what they're saying, but so this formula tells you in practice that if you knew how to compute the modular Hamiltonian of the right, and let's say right side of the CFT, then there's an explicit formula for the bulk reconstruction.
I mean, that formula is very deep. Okay, you're how it works.
Sure.
And I guess you should be able to connect
Whole story of?
without going through the story of even introducing a reflection.
Okay, yes. I imagine that if I take the Faulkner-Leukowitz method of doing it and try to convert that in the language of flow equations and so on, I imagine that I will land on the same formula. But I mean, at least the way I landed on it is right. Yeah.
You're telling us that if you knew how to bulk reconstruct.
Yes. Lambda equals 0. Yeah.
Then this formula tells us how the bulk reconstruction.
Correct. So let's say lambda equals 0 is the thermofield double state, where you have HKLL, you have access to HKLL. So O of 0, I know, let's say using HKLL. Now all I have to do is take that and I have to conjugate it with these modular, whatever, Wilson lines. And that tells me how to do bulk reconstruction around some deformed state. Yes.
So can I say this is like something like the
Yeah, I think that's right.
The difference is what you're.
I think that's right. But
why are you not having some kind of a view?
it's, yeah, good question. So it turns out that these modular Wilson lines are actually very closely related to relative modular flow. They're related to what are called these cocycle flows, which are essentially relative modular flows. So yes, they are very closely related to relative modular. In the view of time, I'm not going to explain that in detail, but they are related to relative modular. Yes, Venta? Oh, that's a good question. Great question. So what happens is that the curvature, at least in this setting, is in the setting that I'm working with, is in the abelian part. There's no non-abelian curvature for these connections. But in situations where there are degeneracies in the spectrum of the modular Hamiltonian, you will have non-abelian curvatures, and we don't fully understand the ramifications of those non-abelian curvature for bulk reconstruction and so on. Okay, any other comments? Okay, great. Please.
This one parameter family of states. My variation theory or what?
In principle, not necessarily. What I'm going to do in the rest of the talk is small perturbations. But in principle, this formula, it's not perturbative in lambda. This is true at finite lambda. All right. How much more time can I take? Like another 50? I have to leave at 6, but can I?
Until you see the whole thing and you have
to. Okay, fine. Sounds good. Sounds great. Yeah, I have I'll be leaving at 6 p.m. this evening. All right. So at least till then I can. Okay, cool.
There'll be enough questions. So.
Okay. I promise I won't go until then. So what I'm going to do is I'm going to take some of these formulas that I wrote down here at finite lambda, and in the rest of the talk, I'm going to try and specialize to a perturbative setting, as you asked. And that's where the aim will be to use some of these formulas to understand this quantum extremal shock in the Engelhardt wall construction. Okay, so at lambda equals 0, let's say we start with the thermofield double state, as we just discussed. So, the thermofield double state has a nice property that it is its own canonical purification. So in particular, the reflection operator there is kind of trivial. It's the identity operator. So there we know everything in great detail. And now, so what are the perturbations I'm going to consider? The kind of perturbations I'm interested in are deformations of the thermofield double state, where we take the Euclidean path integral description of the thermofield double state and we start turning on sources. Okay. Once you start turning on sources in the Euclidean path integral, you move away from the thermofield level. So consider adding a source term in the Euclidean path integral, think of lambda as a coupling constant in that discussion. Okay. What this O operator is explicitly, I'll say in a little bit, but not super important for our discussion. Okay, so this new path integral, the new Euclidean path integral with the source turned on, is what I'm going to call the state psi lambda. Now, what helps in constructing this modular Berry connection, at least perturbatively in this setting, is that for states of this type, the Euclidean path integral states, we know the modular Hamiltonian in perturbation theory in lambda. Okay? So for example, we know what the first derivative or the first correction to the modular Hamiltonian is in terms of this operator that you've introduced into the Euclidean path integral. Okay? There's a very explicit formula you can write down for it. And just give you one slide about where that formula comes from. Basically, you know how the density matrix of the state changes when you introduce this operator in the Euclidean path integral. There's an explicit formula for how the density matrix changes. The only thing you need to know is how the log of that density matrix changes. Of course, that's a little bit subtle because rho and d rho by d lambda may not commute with each other. So it's a little bit subtle. So you have to do a little bit of resummation to write an explicit formula for d by d lambda log rho, but it's something you can do. And once you plug this into there, you get a very explicit formula for the change in the modular Hamiltonian under this coupling. Some of the details are not super relevant. I'm just trying to convey to you the idea that there's an explicit formula you can write down for dk by d lambda. And then you can plug it into our formula for the modular Berry connections and get a corresponding formula then. Okay, so here's a formula, for example, for the modular Berry Wilson line, or the modular, the exponential of the modular Berry connection in terms of this operator O that was introduced in the Euclidean path. All right, so now just to sort of summarize where we are, we've managed to derive some flow equations for the reflection operator. We've managed to specialize them to the perturbative context. The last step, the last few minutes in this talk, will be to use this to understand the emergence of this quantum extremal shock. So, the canonical purification in terms of psi is just R dagger. The psi star is R dagger acting on psi. So what we need to do is we need to compute the 1-point function of some bulk operator in this state psi star. Okay, so let's say, so for my purposes, what I want to do is I want to compute the bulk stress tensor, the 1-point function of the bulk stress tensor, but I'll stay general for now. Let's say phi is some bulk operator whose 1-point function I want to compute, but I want to compute it not in the state psi, I want to compute it in psi star. So you have psi, but then this R dagger is here because R dagger acting on psi is psi star. Now, eventually, as I said, I'm going to take this phi to be the bulk stress tensor. And more precisely, I want to take the limit where this bulk stress tensor approaches the quantum extremal surface, because that's where I'm going to see the shock, or I'm supposed to see the shock. Now, so this computation is more or less straightforward. Okay, so what I'm going to do is I'm going to compute this 1-point function perturbatively in lambda to first order in lambda. So, you take a derivative of this equation, this left-hand side, you get 3 terms. The derivative can either hit one of these reflection operators, or it can hit the state psi itself. So there are 3 terms, which I have rewritten using the formula for the flow equation for the reflection operator, like so. Now, this is in terms of these modular Berry connections. Okay. And since we have explicit formulas for the modular Berry connections, we can sit down and try and compute each one of these terms. This term, the last term, this term just measures how the 1-point function of this phi operator changes under a change of the state. But the first 2 terms are computed using these modular Berry connections. Okay. So we can explicitly sit down, we plug in the first order formula for the modular Berry connection into this equation, and you can take this integral, massage it a little bit, and realize that what you're computing here, because of this commutator, is a particular contour integral. This contour integral is in the complex S plane, where S is modular time. Okay. In the present context, it's just real time because we are working around the thermofield double state, but more generally, this S will be a modular time. So it turns out that this thing computes a particular contour integral. The contour is the blue one, the one going up like that, and then the one going down like that. You can imagine that that's what happens because the thing you're trying to compute here is a commutator. So it's trying to pick out a certain discontinuity across these cuts. Okay, and because so good. So it's tempting to try and compute this commutator by picking up a pole. This pole comes from this overall. In the modular Berry connection, there is an overall kernel which is sitting out front. That has a pole. So it's tempting to complete this contour and pick up this pole. Okay. If you do that, what you get is you precisely get minus the last term over here. And that, if you think about it, that makes sense because what this term does is it measures the change, or it computes for you the change in the 1-point function of some operator on the right. But of course, the canonical purification knows nothing about the entanglement wedge of the right. You've taken the entanglement wedge of the left and CPT reflected and glued them. So this term couldn't possibly have appeared. And precisely the pole contribution from this term cancels that out. Okay. Similarly, if you compute the pole contribution from this term, it replaces this guy with the change in the 1-point function of its CPT reflected image in the left entanglement wedge. Okay. So the pole contributions from these first two terms give you something that you kind of had expected from Engelhardt-Wald, namely that the dual of the canonical purification is just take the entanglement wedge of the left, CPT reflect, and glue them together. Okay, so the pole contributions sort of just reflect that fact. But where is the shock? The whole point of this discussion was to see the shock. It turns out that the shock comes from the fact that in order to do this, pick up the pole, I have to close the contour at infinity. So, I mean, standardly, these contours at infinity don't contribute. The reason is that, there is this, in the kernel out front, there's a big exponential factor e to the lambda, which is suppressing the contributions from these contours, which are sitting way out at lambda, s equals lambda. Okay, so here I've written the formula for this particular vertical contour here. This is that real S equals lambda, absolute value of real S equals lambda. That lambda is sort of suppressing this overall integral exponentially. But it turns out that when the 1-point function you're trying to evaluate is the bulk stress tensor, this is too quick. This is too quick because the same lambda, or the value of the value of the real modular flow that you're doing also appears here as a boost. Okay. So what's going on is that this lambda there's an e to the I lambda k sitting around the stress tensor that is boosting this bulk stress tensor away to infinity. Okay, because it's boosting it away to infinity, the correlation function will also exponentially decay. So of course, this vertical contour will decay exponentially in general. However, there's a caveat to that. When x plus goes to 0, namely you sort of start to approach the quantum extremal surface along x plus, the operator is not boosted anymore. Okay, because x plus goes to e to the lambda times x plus. When x plus is 0, it's not getting boosted away anymore. And furthermore, from these plus plus indices on the bulk stress tensor, you're getting an enhancement. So because this operator is carefully tuned to have these plus plus indices, you get an enhancement in S or in lambda, which sort of which overcomes this exponential suppression out front. Okay, so when x plus is not 0, this vertical contour decays exponentially. When x plus approaches 0, it blows up because of this enhancement, and then so that signals a delta function. And then you can work out the coefficient of that delta function, of course, by doing an integral in x plus in an infinitesimal interval. And by doing that, what you find is that you find that the coefficient of that delta function is precisely this delta S bulk by delta X plus. Okay. So going into the details of how the coefficient is equal to this term, I will defer to discussions. If you have a question about that, I can answer. But what I've tried to convince you here is that you get a delta function shock from these vertical contours at infinity, and those contours, the coefficient of the delta function shock is precisely what you expect from Einstein gravity. Yes.
Take a spin system. All these things.
Yes.
So we just reconstruct some paper.
Hmm.
Do you think there will be shock there also?
No. So right. So this is in a holographic CFT. So I guess at some point I sort of transitioned. So much of this is general, but when I'm trying to compute, let's see, when I try to compute this particular correlation function, I'm using bulk techniques to do that, right? Because first of all, I'm computing the 1-point function of a bulk operator. Secondly, I'm using here the fact that around the thermofield double state, boundary modular flow equals bulk modular. Okay. So I should have said this explicitly, but at this stage, the way I'm computing it is I'm using the fact that this operator here, which is actually boundary modular flow, around the thermofield double state, I can trade that for bulk modular flow and then do a bulk computation. So it's important in this calculation that there is an emergent bulk, a bulk quantum field theory. Which is where the properties of this boost and the corresponding enhancement and so on, they come from the fact that there's an emergent quantum field theory. No, presumably not. I mean, with some maybe cutoff version of a shock or something like that. But not a delta function. Presumably not a delta function shock, but some sort of cutoff version of that, like a smoothed out version of that. Yeah, we can. Sure. But that's a good question. Whether doing a finite n calculation gives you some kind of a smoothed out shock. That's I think a good question. Okay, so I'm sorry that I've gone on for so long. Let me just wrap up with one last slide. So at least I hope that I've tried to convince you that the set of tools around the canonical purification and the reflection operator are useful tools in ADS CFT, in particular in terms of bulk reconstruction. They go beyond standard entanglement measures. In this talk, I've tried to give you a construction for this reflection operator in terms of a flow equation for a 1-parameter flow of states. We use this 1-parameter flow equation, at least in a perturbative setting, to derive this quantum extremal shock that was predicted by Engelhardt-Wall. And going ahead, it turns out that there's also a replica trick construction for this reflection operator that is useful. So where we would love to go with this is that we would love to use this replica trick construction in order to compute something involving the reflection operator that would allow us to probe the complexity of bulk reconstruction. And this goes back to the question that Ashok had asked at the beginning of the talk. So I'll end there. Thank you.
Thanks, Onkar. Are there more questions?
From what you said, it looks like for finite and it will get regularized, right? I mean, that doesn't seem to be any scope of getting shocks for finite.
I agree. Yes, I agree. I have no, I mean, I don't, in a perturbative computation around infinite n, I don't think it will get regularized. But if you strictly work at finite n, I think that it should get regularized. And I think that would be wonderful to understand how that. Yes, I think that exactly. I think it will regularize the shock. Yes. Okay, so thank you. Yeah, thank you.